what's the weather today? Hey, how's the weather to traffic to airport? I should just communicate. Why should I go and open up a screen and type ChatGPT prompt or Google Maps and do all that? So there's a lot of focused audio coming up there. So we have a notion of agentic AI. This is not a talk on agentic AI. I want to get into that. But literally, if you want to make really intelligent context-aware AI agents, audio perception is equally important, but ignored in the field. So that's my whole point of this talk. So here's an example of, you have somebody teaching a robot how to cook, but how you audio cues, when your spatula hits something like this. So for a robot to, actually the haptic feedback is not very good. It relies on audio cues to figure out that the spatula touched the pan or something like that. So you really realize audio modality quite well effective there. And of course, there are agents that can hear and speak. I'll give you example in ChatGPT 4, we can do that here. And there are a lot of tasks, So we're living in an era, in good old my old days, when we used to read paper, we used to go and photocopy papers in a hard copy, read it. Then came the PDF world, right? You can read paper on your laptop, on your PDF. What is happening? Now if I tell my student read 10 papers, they don't read papers. They take the 10 papers, go to ChatGPT or Acrobat, summarize it. Walk me through 10 papers, right? So quickly, like one paper for 5 minutes. That's a new, and I'm sure you get all ChatGPT reviews, right? So we all know what happens there. That's text. Text has come a long way. I said, go watch lecture. Who has the patience to go and hear 1 hour lecture? So what if I tell you, go summarize a lecture? Or summarize a movie for me? So if you do something like that, if you ever want to take a long video, YouTube video, summarize it, the audio cues in a movie or in a long video plays a very big role where the context is happening. So if you take audio-visual data, the understanding audio cues in a YouTube video or in a movie are very important there, right? So audio can also impact the context. This if you go in AR, VR, if you play game movies, you can never enjoy a movie without the audio. You can never get a scary emotion or like some background monotony, some mood they want to convey. It's known audio plays a big role. So this is where audio comes up. And here's an example of, when 2 years ago DALL-E came. This is generative AI video. So you can see this is a video just from text to thing, show a map here. If you just generate a video with no audio, there's one impression. But if I generate audio separately and superimpose that, you see how the perception will change. Now same thing, but if I put audio there, all of us love music, Indian music, Western music, all kinds of different culture, wonderful music. So you see how much audio and music plays a role in your life. So this is all about it. So this is not a new idea, especially with all the machine learning bubble that we have seen last 15 years. A lot of work has been done by academic community, research lab, industry. So I'm not going to cover that. So people are doing scene understanding, and which is a very big fundamental problem in computer vision, robotics. Audio plays a big role there, especially there's a whole notion of egocentric perception. We're getting egocentric devices, human action. I showed the example of cooking there, screen captioning, and all that stuff. Agro comes here. So here's the example, right? If I show this image like this, if there's no audio, you just with the image, your caption will be, oh, I see a black dog lying on the sofa. But if I show the audio, right, you say, oh, there was a living room with a black dog on the sofa barking, the sound of police car in the background. So suddenly when there's more audio cues, you can know much more about what's going on there than just with the visual only. That's a known fact. And if you play with ChatGPT 4.0, actually ChatGPT 4 is getting pretty good. ChatGPT and Gemini, I think, are the state-of-the-art system with audio thing. But here example, I'll show you the video. So ChatGPT can hear and speak, so you can converse with it just like anybody else. Here's an example of a ChatGPT 4.0.
Hey, how's it going? I'm awesome. Listen, I got some huge news. Well, in a few minutes, I'm going to be interviewing at OpenAI. Have you heard of them?
So it's getting there, but it's mostly speech data and only certain languages. That's what ChatGPT can do. So you can have a conversation with all the time. Now, of course, as I told you, visual task, if you look at any of the tasks, so in the computer vision community, there's a whole area called audio-visual recognition that not just say camera data, but combined with audio data. So scene understanding much better. Understanding, even speech understanding, speech separation, all the classical problems, if you have the visual and audio, you get much better answer, much better accuracy with this. In fact, the new device like Alexa from Amazon they have camera as well as audio clues, and they do a very good job of that. So this is the way the world is moving towards audio-visual world and how things happen there. So you also video question answering. This is a classical computer vision. And here's the example of, suppose, a robot navigating. Of course, robot look at video. But here's an example that you not just have a camera, but you also have a microphone. And in that case, the robot is guided to a navigation. You'll see how the audio cues help in a minute. So sometimes the audio comes, it helps you find the source. So just like if you go somewhere in the house, you're driven by the audio sound, and this is where we're heading towards. So clearly, what has the world gone? So if you look at the last few years, just like all parts of AI, machine learning, language, vision, audio are really exploding. But I will say the audio intelligence system have seen a long way, but compared to NLP text and vision, audio is the least studied of the three. Text and video are much ahead, and audio is less. And hopefully, my hope is to convince you do more audio research, because that's an understudied thing. In computer vision, there was something called CLIP, which association with visual cue with text, because text was the first thing NLP did. Then CLIP came. So similarly, in audio world, they're called CLAP. So replace, CLIP was image to text, CLAP, A stands for audio. So that's been done. Some of the work is done here. Compay for my group, I'll show you more about that. And there are some audio LLMs. There was LTU, very famous, and a Gamma, which came out of my group, published last year. I'll tell you about what they are. This is all about audio understanding. So here's an architecture of some LLM, how the architecture, I'll talk more about it. And literally what they can do is the following, that if you see the thing. The second is generation, that just like all the diffusion models can generate images, people are trying to generate audio. So the question would be, right, when can computer generate good music? When can AI system can they really make good music, right? That's a big billion-dollar question right now. We can all talk about it. Human is intuitive, can't beat, but we're getting close to what computers can do there. So this is where a lot of music generation comes up there. I'll tell you what the challenge comes up here. And this is, for example, a diffusion model. You give it a query text, like this is spatial thing. Let's recreate a gentle rainfall with distant thunder. And let's see the audio output it gives to you. So for simple thing like this, generative AI has to come to a stage. You need some audio sample, don't go record it, don't search YouTube. Simple audio, generative AI can do it. Not bad, right? We'll see what happened to complex audio there. That's what this talk is about. And then there are a lot of speech generation model as well as audio storytelling. So this is where you see a lot of commercial interest. In fact, people are saying in the LLM world, there are more investments going into, there are a lot of VC funding going in this area where people are building systems. This is one of my examples, right, of storytelling. So this is an example of, can you make audio storytelling, such as this a wave journey? Here's an example of a totally generative AI, and you can see how good it sounds.
Good evening, ladies and gentlemen. This is the BBC World Service broadcasting live from the heart of Paris city lights are, it seems, ever deepening mysteries. The date is June 1926, and we have a rather unsettling story to share with you tonight. A local artist, a prominent figure in the surrealist movement, has mysteriously vanished without trace. Known for his avant-garde work, the artist was last seen on the mountain.
So it's interesting, right? Of course, the age of audio fakes or deep fakes, what can you do? But this is tell you where the state of the art is. This is simple speech audio. It's like basic simple version of that. So let's keep going. What are the challenges? So I'll tell you why it's one of the most challenging areas, especially compared to NLP or vision. Audio is very understudied, and that's what I want to really emphasize today. So, two things for any machine learning system to have. One is data, second is compute. That's the state of the art in machine learning, right? I'm not advocating that's the best way to do AI, but today, all so-called good systems, you need a lot of data and you need a lot of compute. Of course, Jensen Huang loves it, right? You're selling all the NVIDIA GPUs. So compared to other places, audio data is much, much, much limited. So give you an example of how much data sets are there and where things are going. If you look at language, right, so basically all this language model, like ChatGPT, Gemini, they use a probabilistic model using auto regression to predict the next token. That's how they one token at a time. And sometimes a lot of them get good results, but sometimes it creates crazy results because hallucination. So when you train them, based on all the text data on the internet, there are billions of tokens. Maybe that's the reason ChatGPT a lot of people like, because it gives decent answers most of the time, because trained on large data. When people go to vision world, you look at vision data sets, especially people use YouTube, all the images that you post on social media, Facebook, WhatsApp, Meta has access to them, they use for training. Again, you got about 5 billion sets. So look at this billions. Let's go to the audio space. Remember I told you about speech and non-speech? This is speech, and of course, speech is, there's so many languages, right? And in India, which is the most diverse languages, we'll talk about that at the end, 22 official languages, and if I saw somewhere, maybe 300 unofficial other languages variants. The best speech data set in any language is about 60,000 hours. Look at the scale, billions to this. And if you go to non-verbal data, non-speech data, non-verbal, this is the data set we have. And this includes music, environmental noise, all kinds of noise you hear in nature. So you can just see what the thing is. So this already tells you, if you want to do great machine learning on audio, get the data. And you need big bucks, and big companies are doing that. Secondly, it's not just audio, right? Simple. One thing in my talk I'm going to talk about is complex reasoning. I'll show you complex audio. What does it mean? Like not just one single speech or one single sound. And unlike language and vision, distilling larger model is still a very open area. In fact, very few systems can even process an audio sequence of 30 seconds. Forget the one long video. This is state of the art right now, especially non-simple. So here's the example I show you.
I'm tired and I want to go to bed.
So this is a simple event. You hear somebody speaking, and what sounded like a blast sort of thing. Simple event. So this is what we can do. If I ask you a question, what are the acoustic events of the given audio? You say human speech and some, like a gunshot or something. But if I ask a complex question, from the speech and impact sounds, could you deduce the size and kind of the room? Was it a big room, small room? Can anybody guess? Now, humans are very good at it. Are you speaking in a small room, big room? This reverberation tells you a lot about it. Current audio instructions can't deal with this kind of situation. That's where machine learning fails. Long audio, right? So most data sets have very small clips, at most 5 to 10 seconds. We just did data set to 5 minutes, but especially non-speech, this is the state of the art, very primitive, right? And of course, we use a lot of audio encoders. Now, the computer vision community, in the last 10, 15 years, they were the classic benchmark ImageNet. If you look at the best visual encoders, they're traced on ImageNet, traced on YouTube. Because a lot of visual data, they can do up to 98% accuracy, 95, 98. But the best audio encoder, still only at 50%. So does it mean we need more data, we need better architectures, or maybe both? But that's where things are right there. And especially with compositional audio, I'll show you language variation. Models cannot do it. So again, I'm giving you all the challenges about speech, sounds, music. They're all treated separately there. So this is the whole idea of that we need better benchmark for understanding and reasoning. That's a really golden challenge in this domain right here. So I say there are a lot of audio model proposed, especially this field has taken a lot of things. Especially real world audio is compositionally complex. How do you generate and train them? So for example, you give a caption, you say dog basically barking followed by a person speaking. So something like this, you can actually generate it also, and you can also do understanding. This is like a simple audio, I call it. But let's say you take more compositional audio data or better model architecture needed, it gets much harder. I'll give you some more example here. Second thing is, if you're given complex answer question, right? Let me give you example of this right here. Let's hear the audio. So you heard that audio. Can anybody guess what it was? It's pretty complex, right? You have to listen again, attention. And if I ask a question based on various sounds, your audio understanding system, what the man might be announcing, best audio listeners say we can't figure out. So there are a lot of complex sounds. Sorry, we can't do it. So we need more benchmark, better reasoning data, and ultimately, as I said, we need deal with large audio, because in real world, You can hear music playing, you can hear traffic noise, all kinds of audio. People are recording sounds all the time. You want to process them. Here's an example there.
Hello? Anyone here?
Okay, so somebody. So, you know, if you play an audio like this, what's the moment of fear in this audio? Again, not easy to do it. So this is audio generation. This will fail. The second part comes out to be long encoders. Again, all the open problems. Hopefully, you're seeing a lot of challenges here. And second is what this being notion of audio language models. So this is the real part of what we're doing. LALLM. You got LLM, VLM. So some people call it ALLM, audio large language models, or some people call it LALM, large audio language model. What's the core idea? So literally, you know, we want to do understand, generate, interact with audio data, just like we do with text. ChatGPT can summarize documents for you. ChatGPT can write your emails, write your paper reviews, someday write your papers. We're getting close to it. So that's what we want to do. And the idea is that our audio data is much, much smaller, right? Billions to like tens of thousands. But language is basically a thing. So literally, we're trying to pick up the data gap because we run a lot of language. So ALM's audio language model basically learned a shared latent space between audio and language modalities. Because we run data, so we are designing a whole latent variables idea, doing that here. Now, this is not an idea. If you look at before LLM became popular, as I told you, there was a very wonderful work in CLIP, which is very people in computer vision know, image versus text. So they extended to CLAP, which is audio versus text. So this was before LLM came up, do it, and it was used for classification, audio text retrieval, and text to audio. Here's a typical CLAP model. You know, how do you pair audio with text? And based on this metric representation, you can do a lot of inferring. And now the LLM became popular after ChatGPT. Suddenly, we have the post-LLM era. This leads to what is called LALM, which is what we're working on right now, integrating audio encoders with LLMs, undoking. And here's some example. There's some model from us, from Microsoft, other companies. And you can see they can do captioning, reasoning, and open-ended question answer. I'll show you the state of the art, but still how far we can go from here. So here's the current state of the art language models. And just like any language model, there are three categories. There's open source, right? There are a lot of people like academics. We love open source. Jan LeCun loves open source. DeepSeek did a great job open source. So these are open source model. There's some from our group, Gamma, and there's some NVIDIA, Audio Flamingo. These are all open source models, which means you can get the code, you can do good research. Some of the most sophisticated models, guess what? They're not open source. The Googles and the OpenAI, you know, ChatGPT and GPT-4 or this thing. And then there's a third category of what is called, you know, open access. It's somewhere like between close and this thing. So there's a model coming from China, you know, Qwen2 audio chat is instruct. So clearly you can see the academics group, and there are a lot of big companies, you know, of course the Google and OpenAI have huge resources along this thing, and they can definitely do a lot more stuff. This is really ongoing work. So I'll tell you some of the problem work we have done now. Hopefully I motivate you enough to see one of the challenges we're doing. So we're working on compositional reasoning, an audio language model. This was the work we presented last year, ICLEAR right now, you know. So the idea is that, remember the CLAP is to association between audio and text. We're especially looking at the relation between text in caption and the corresponding audio as a fundamental goal. So ultimately, how you give input text word order usually lead to different perceived audio. That's a very fundamental problem. This is what we're trying to address right here. And if you look at the state of the art, we found the benchmarks were lacking. I will not go details of that for the lack of time, sorry. But literally, you know, and ultimately conclusion was all the LLM I showed you, ALM before, they're good at simple audio, but you got compositional reasoning, they were pretty state of the art was pretty bad. And that's one of the goals we want to do in compositional audio. So this is the first work we started to do compare. And literally, you know, to do anything first, what do you have to do? Since there were no good benchmarks, we spent a lot of time with a big team generating a benchmark called compare. It's the first suite of benchmark can do compositional reasoning. So the two parts with compare order, which allows ALM to understand the occurrence of between multiple acoustic events, and compare attribute, which understand binding acoustic multiple events. So you can make complex audio means there are multiple events. There could be a dog barking, baby crying, all kind of music sound. So you want to understand the relationship between them. That's what we're trying right here. So this is the example of a compare order. If you can see at the back, there are a bunch of audio compare here. So if I give you like this, complex audio, a tiger goes followed by people talking, right? So you'll see what happens here. you don't hear too many audios, like tiger growls and people talking. They're very simple acoustic events. So this is a classic complex audio where you can literally not do it. This is a benchmark here, right here. And then you can see other way around, people talking with tiger growing. So we create a lot of benchmarks with multiple acoustic events, so really have more complex and see what we can do. And there are attributes, which is basically something like this, which is about understanding attribute binding. So here's the example of a child sneezes and adult laughs. You don't hear too many audios like this, so we create benchmarks like that. Sorry, let me just. Okay, this is. So again, you don't hear sounds like this, child sneezing, adult laugh, and you see how it comes up here, and a child laugh, adult sneezing. Again, similar kind of benchmark. So we create a complex benchmark like that so people can do some compositional audio. This is the first attempt. There are other benchmarks like this. And this is how we do benchmark evaluation. So the idea here is that this is not too many equations to show, but we look at the benchmark like this. We do the test scoring, based on this kind of formulation here, probability formulation, the audio scoring. And the whole idea is since you're binding text to audio, you combine the two and you got to combine score. So this is how we're doing better bounding and figuring out the relation between complex events. And literally, if you see all the previous benchmark, including clap and variance, these benchmarks, they cannot do it. That means the previous work just could not do compositional audio with multiple complex events. This just showed you how the state of the art was there. Here's one of our benchmarks, we release. It's not huge, but for academic standard, it's not bad. 661K, and you can see, different kind of events we have, like the blue means one event, green 2 events, and some 4+ events. So more events, more complex means. So if anybody wants to work on this, you got this different complex audio sets here. More events is challenging, that's what helps there. And this is our extension to CLAP, the famous model that now we want to deal with complex audio, so we do 2 algorithms to enhance the compositional representation in CLAP. That's where we go from it. And literally in each approach, each audio sample assign hard negatives, and that improves distinguish. So this is like I will not go details of that, but literally coming up with a whole compositional extension of CLAP to show we can do complex audio with similar thing. And here's the whole formulation. I can refer to the paper. You can see the details of how the compositional attachment reasoning is done right here. So this is ComP-CLAP. Again, a lot of training strategy, template-based approach. How do we deal with complex audio? If you do training, everything, the architecture has to go along, take into account. This is also to generate synthetic data because it's very hard to capture real data. We take some real world samples, generate samples like this. I'll talk more about this slightly. You'll see how complex audio comes up here. And then you get more examples like this, basically model of contrastive learning, how you can dealing with ComP, which is again an extension of CLAP, and this is the basic architecture looks like. Again, not too many equations, but I can refer to the paper for more details about that. So here's some example. If you want to publish in any machine learning conference, machine learning reviewers just see lots of benchmarks and lots of evaluation. If you write, the typical review is do more 10 more comparisons. So anytime you write a machine learning paper, you go and do it. So here we showed some previous model, MMT, CLAP, CAP, Leon, ours to ComP-CLAP. And you can see, that literally we do benchmark data sets, and you can see our numbers are significantly better based on our previous model. This was the first one which can do what we call compositional audio right here, getting much better results. And this again, on different models right here, comparison zero-shot audio classification without any training. And again, we are seeing much, much better numbers than state of the art right here. So I don't want to bore you with numbers, but just keep on saying there's a pretty significant improvement. So this was the first audio model we introduced last year for complex reasoning, which was presented at EMNLP last November. So literally, as I said, most previous LALMs, language model, were doing simple audio. They cannot do multiple complex events. So this, to the best of our knowledge, we try to build the first complex model from ComP. It's how do you user queries with composition reasoning. So let me give you some example of this and see how it happens. Here's an audio sample. So this is a long audio sample you saw. And here is the example of how it works out. So it's a previous work on simple LAM. Here's our architecture gamma. There's a big encoder here, and the 3 components of those machine learning can recognize them: the aggregator, Q-former, and soft prom. took this the basic architecture we proposed to deal with compositional audio, and our initial results were quite promising to show that it can do much better job of this. In the interest of time, I will just let you deal with it, not details. Here's just overall architecture I showed you here, large language models. As I said, there's a multi-layer aggregator, audio tube former, and soft prom. And the whole idea is to combine them together to deal with complex audio. This is just, I believe, with the details. The paper has a lot of analysis of architecture, why we chose it this way. So here's a reasoning data set. It's on 2 stages. First is pre-trained on a large data set, instruction tune. Well, we did gamma first. We did not a lot of post-training, which is a very popular thing in LAM world right now, but it was just based on pre-training like this. And again, you will see different kinds of situations we dealt with here. Again, in the interest of time, I'll just go in the details about that. So here are some benchmarks. As I said, right, any machine learning paper, you got to have lots of data sets. So on the left, you see different audio models from audio clip, clap, to our gamma with different version. You can also see we did different because we have 3 parts to it. We do ablations with 3 different studies. But you can see, it's a big numbers. All the bold-faced numbers are showing that on the complex audio data sets, we're getting much, much better improvement over state of the art. I'll just leave it like this to show you example of that. Let me show you a few examples here before we get into it. These are reasoning data sets, again, showing big benefit on that. And here's some qualitative example. So, just an example of what's showing on. So I'll basically, let's say, play this audio. So you heard the audio, and if I ask a question, based on the given audio, input the type of environment or setting, and consider present duration of car sounds. So here are the example from different audio language models. So LTU says, it's this urban suburban environment with a mix of residential commercial areas. Salman, another famous model from Alibaba, says something else. But our conclusion is saying this is likely a racetrack. So it's a much better estimation of the same audio than the same method. Let's play another one of these. So let's play this audio.
All these are just little tricks to make you sound more like a voice. True.
So hear this audio and ask a question. Figure out the connection between man's speech and the music. What do you think is going on with the music in the scene? And again, somebody said just music. Somebody said crowd reaction. All kinds of things. But we get a better estimate. It's likely a guitarist or instructor who is explaining the process of tuning a guitar. So again, this is the kind of complex audio, and you can see, hopefully we're doing much better in terms of inferring than state-of-the-art model. That's what gamma can do. Now, this is, of course, complex audio. As I said, the hottest thing right now in LLM world is understanding and reasoning. So this is basically, if you talk to somebody, AGI, and I'm not going to stand behind the definition, I'm just quoting that they want all the system do what they call 90% human scale. That's like a very crazy benchmark standard. But even if you look at, the current audio benchmarks, they're way, way, way below 90%, not even a kid. So in the NLP world and vision world, there have been 2 big benchmarks, MMLU and MMMU. So any paper on audio visual language model now has to show the reasoning and what understanding on MMLU. So there was nothing for audio world, so we say, okay, let's build a benchmark, just something like this, which can do the most comprehensive audio understanding as benchmark. So this is, again, we built together a lot of effort, 10,000 things with created audio clips with natural language and speech, environmental sound. So the benchmark here, again, I don't want to go details of that, but it's a lot of question answering. It's a huge benchmark effort. You can see the speech samples, sound samples, music samples, and if you see the big colors, they're different kinds of sounds. So it gives you a very diverse data set to do something like this. And again, without going details of that, you get all the scores. But literally, we found when we build this benchmark, audio reasoning, all the benchmark, including one from OpenAI, Google, all the Alibaba, big giants, the best of them have pretty poor accuracy. So what does it tell you? That even the best of open language models does not do a good job audio understanding and speech and reasoning. This is an opportunity for all of us right there, still pretty low. So this led to what we can do. Again, you can see here more examples. So this is like different kind of audio samples, and literally the essence of this is that current state of the art, even Gemini 2, Google has a huge group working on Gemini group, Google resources, but guess what? They're not doing really well out here. So then one of the things we try to do is, since capturing real data is very hard, not easy, in speech community and other places, they actually found that if you take real data and augment with synthetic data, it's real plus synthetic really improve the thing. So the question is, how can we take a data set and combine with synthetic data? There's another paper presented at ICLR later this month in Singapore. So in the interest of time, I'll just give a high-level idea that basically we propose Syntheo, a new way to augment real data with synthetic data to generate more diverse and things. Some of you probably work with NVIDIA, Robotics, Cosmos. They have the same philosophy. You take some real data, do it. The challenge here is the following, that there are a lot of attempts like this. If you generate a lot of synthetic data, it's a diminishing return, like we saw this for vanilla synthetic argument. So the idea is generate more augmentation. Ideally, I wish the growth was linear. It's not, it's sublinear, but we're still getting better performance. So classification accuracy is still improving. That should show the benefit of synthetic data, Syntheo, on the red is on the shown right there. Actually, we were using 512 GPUs at NVIDIA. I don't have 512 GPUs, H100 at UMD. I'm poor compared to them, and doing training with a lot of this stuff there. Did we long and short videos here? I want to show you some examples before we move on. So literally, skipping very quickly just to give you all the components of how this architecture works, how to performance optimization. So this is a lot of building a large scale, audio language model. We take a lot of engineering as well as a lot of fine tuning to get it right. Here's the training objective, which we show the formulation for training objective, we go there. So just let's see example of a few things what we can do. It has a big data benchmark called audio skills. It's part of large synthetic data benchmark. We want to do with the long audio. That's what example it does here, general counting. Apologize for going over very quickly in interest of time. Long audio understanding, the first one which can do long audio understanding. We got quite a few samples, 260,000 versus 80,000, lots of diverse audios. If anybody wants to work on this, you have a data set now to play with and evaluate that. That's how machine learning research progresses. And the last is all this kind of long audio. Let me show you some examples of models here. So this is comparison, where we come up with audio like this. So the last one is ours. And you can see, how much we are performing expert. It's a huge, huge improvement over state of the art. So let me just show you some example of audio Flamingo can do. And hopefully, if you want to have fun with audio, you can do it. So this is I'll play audio sequence here. It's a long audio. So you heard a long audio, about 6-7 seconds. So if I ask question, what is unusual about the audio? Now the actual answer was, it contains of music and hammer beating. It's like you don't see music and hammer beating, unusual. So we do it. Let's see how other people respond to the audio system. If it was LTU, nothing unusual. Quen2 gives an energetic experimental mood. Even our previous work, Gamma, does an unusual sound. But Gemini, Google version, you can read what's saying, fast, consistent pace, making all kind of reasoning. And of course, our audio Flamingo 2, not perfect, but gets very close to the ground truth. You can see how much our answer blue matches the green. So this is an example of how different models interpret complex audio. Let me show you one more example here.
A regular question coming up is, what's the cheapest smart trainer that I can get to use Swift on? Well, I've answered that in my blog post about the Elite Cubo digital smart. Well, hang on, I'll link to my blog post and the trainer itself. I thought tonight I'd put the Neo and the Kicker aside and jump on the Elite Cubo digital smart beat. It's a tough one. There's about 17 different trainers they make, but I'll link below and I'll put in the description what this trainer actually is. But it's the cheapest smart trainer you can buy. I'm going to give this tonight to the Aussie Hump Day Ride, which is the biggest community-led ride on Swift. I want to give the experience of that. This will be my first bike ride on the London course. Will I be able to keep up? Will the train perform? Will it be too noisy? What's it all about? So about half an hour ago, I just set it up now. It's very easy to set up. This train isn't a direct drive, it's tire on.
Pretty long sequence, everybody getting bored, right? So
Super strong, so it's just.
speaking, music, speaking,
And the way you want to saddle,
this goes on, right? So
and as long as your tire pressure's up around
if I play you this and ask this question like a quiz, when is the song with the music vocalist heard? Towards the beginning, in the middle, towards the end? Of course, it was the middle. Speech, music, speech. If you look at different versions, we get different answers here. So literally, you know, if you look at compared to all the previous models, even a very long sequence, because they could not process it right, you will remember there was a long speech, music, long speech. So we do much better job of detecting this. So literally, you know, let me conclude since my time is running out here. So I'm hoping I'm convincing you to do, you know, that this whole area of audio, especially we do LLMs and VLMs, text has made a good progress. It's not a solved problem. Video has put a lot of progress. Audio was like the stepchild. And hopefully, there's a lot more effort. In fact, a lot of saying next 2 years, all these companies are putting big resources. It's a good time to bring audio. But if you do audio understanding and generation, you know, one thing we tend to understand is, can audio generation and understanding help each other? You know, understand audio generate, look at them independently, but not really done them very good job. And ultimately, you know, how can we build model which can deal with complex audio and understand and generate audio at the same time? That's number one. The whole question about is, you know, the so-called AI question or whatever it is, can we scale inference time compute for audio generation? You know, inference time compute has been a new trend, and if you know, NVIDIA loves it because it takes more GPU resources. But what actually even DeepSeek has shown everybody else, that you could do better reasoning with inference time compute. It has been shown for text and video, but it has not been shown effective for audio. So this is again an opportunity for us to do something here, and of course make the audio language models more efficient and complex reasoning. Now, since I'm giving this talk in IIT in India, for those of people who are from Indian research, I want a little bit talk about the fact that, you know, doing this kind of research, especially in a country like India, where I'm from too, has a huge market. You have a very large smartphone user base. I've seen some people saying 800 million users or 700. There are a lot of people, a lot of them are not very educated. For them, they actually interact with their device, smartphone, using audio. Like you ask a question, right? Audio query, like audio GPT. So, and there's a lot of demand for educational entertainment content, and you have a lot of language markets. So one challenge of India is that it's a very diverse country with different languages. And while we have a lot of data for English, Indian language are very low resource, they have very little data. So you've got a lot of languages, a lot of diversity, less data. So this is a huge market for academic research and even commercial players to do a lot of research for all this educational and other kind of entertainment to do it. Now, literally, you know, as I said, one of the challenges they're facing is that very limited availability of data. Data is very limited. Even if you look at the best Indian ASR system, speech recognition, compared to English or Chinese, the Indian systems are much, much lacking. And you will see some papers like that. And there are all the challenges of dealing with right here. So this brings up a big question, you know, that the notion of audio LLM can help a lot, India a lot. So this is all the reason. In fact, I should also mention too, we're actually working with 2 big companies, commercial companies in India, trying to see how we can develop LLM. So it's a huge opportunity, right? You got a huge user base where voice first is a big interface they have to the device. You got the challenge of big languages, multiple languages, and low data. How do we do it? So let me just stop here. Let me thank all of our sponsors, especially all the people from, you know, industry partners we have. You cannot build this model with industry partners. So I'll just stop here and see if I have time for any questions or feedback. Thank you very much.
Thanks for the talk, Professor. I have a question. Like you mentioned about text captions and audio, they being sharing some latent space.
We have to build that data space. That's
Yes, yes. So what I personally feel is the emotion that's there in the audio is not maybe not exactly explicitly present in the text. So is that the gap, or is there something else, or is there something even more?
That's a great question, the 2 parts. So, you know, audio, as you say, conveys the emotion.
Yeah.
In fact, it's the best cue to convey emotion, besides facial expression. You can see somebody's angry or not. But I could talk to you on the phone, and I can see you're upset at me, or you're angry at me, right?
Indeed.
So in fact, honestly speaking, we're actually working on a follow-on version to Audio Flamingo, which has the emotion component AF3.
Okay.
So that's, my current system doesn't do a good job of recognizing emotion. but we're working on system.
Okay.
So that's just itself, because a lot of our speech and audio emotion we're doing. The real question you're asking is, so we don't have audio data, a lot of language data. But as you're saying, in many ways, audio conveys much more than language can. Like you can't read a sentence. Yeah. Sometimes you can see from the language the person was angry or not,
Yes.
but audio conveys much more.
Yes.
So, given the different nature of the modality information they convey, audio is much richer modality, just like visual art. So how will it do the latent space? So, honestly speaking, we are still in the early days of audio LLMs,
Okay.
and I would say people should develop that audio latent space which actually fills this gap.
Okay.
So it's by and large still an open question,
Okay.
but a very important one.
So, like you explained the architecture wherein you were doing LoRa fine tuning and all.
Right.
What's your opinion? Do we need a specialist architecture or fine tuning with a specialist sort of PEF technique could be sufficient enough, or the existing PEF techniques from language or vision could be?
So, as I said, if you look at the space, people had first successful language,
Yes.
ChatGPT, right?
Yes.
We did clip,
Clip.
go to visual.
Yes.
So, okay, we should do clap, right? Clip to clap, being audio, right? So, a lot of our architecture, like I showed you for this, they kind of follow a pipeline. But one of the things we have actually found, and maybe, as I said, if you look at the computer vision research, like ImageNet, and even talk to Google Gemini, the visual encoders are much, much richer. So, compared to audio encoders.
In terms of
Recognition.
in recognition. Okay.
So, like I told you, ImageNet is 95%.
Okay.
But the best audio encoder is still 15-16%. Now, why? Maybe they don't have data to train, or the architecture's fundamental limitation.
Okay.
So again, the question comes up. So the first component of all the audio encoders, which is like a fundamentally signal processing problem, and I think we need more research.
Okay. And one last question. For reasoning part, have chain of thought prompting of this type of techniques have been explored for this particular purpose?
Yeah, chain of thought is a very popular technique. In
Yes.
fact, some people are doing it. Audio space, not yet.
Not yet.
I'm not aware of.
Okay.
So I think clearly everything that has seen success in language and vision is natural to an audio space, including chain of thought. But as I said, this has been a stepchild. So I hope all of you work in audio space so we can really enhance this area.
We can have one more question.
Hi, thanks for a nice talk. So images are more stationary and audio signals are non-stationary. Moreover, the stationarity period is limited. So can we apply the similar models to the audio signals and do with it? The second part is the instruments and other things can be, if we divide into two parts, maybe we can do better in audio also. Thank you.
So the two questions. You said image is stationary, but videos are not. Right? I know. So you're looking at a single image, but YouTube
But
is-
video also has an image component. So we fuse two things so we
So
can
you
do
think of this way,
better.
right? So yeah, you can think of high level thing that a video is a collection of images, right? And in audio, but see what I was doing, audio was motion event. Remember I was showing you this a baby sneezing and a human talking, right? So literally we were doing like, okay, this is baby sneezing, this is human talking, this is dog barking. So in audio we have a better notion of events. Because there's a big discontinuity, like baby sneezing, human talking, like two very things. Whereas most video you see, you will not just show a clip from Delhi, and a clip from New York, and a clip from London. So I would say that in the video space, temporal space, at least there is more coherence, which do. So audio has slightly more, you hear a sound and this is sound. So audio has more of these jumps. And in some way, that's probably one of the reasons I'm conjecturing why we don't have good encoders, because they create new challenges.
So if we divide them into different spaces, maybe we can
Yeah.
do
So if you can take
better.
a long audio and you could, this is event one, event, if you could somehow classify the events, like like in our benchmark we have 4 events. If you can take a long sequence, like think of a live dialogue or a movie thing, and if you could decompose into events, you're 80% done.
Yes.
So that's exactly one of the biggest challenges we're dealing with.
Thank you, sir.
Thank you, Professor Manucha, for the exciting talk. Our next speaker is Professor Alfred Hero from University of Michigan. He is going to talk about optimized recalibration of pre-trained machine learning models. Welcome, Professor Hero.
Right, that looks good. All right, great. Let's see. I'm not sure how to bring up my talk, but let me just get started by, like the previous speakers, thanking the organizers for inviting me to this, especially Vijay Mishra, who I have I'm disappointed he couldn't make it. I'm going to be talking today about a problem that arose as a pretty much a direct consequence of dealing with the problem that modern AI and modern machine learning has effectively turned a problem of understanding, retraining, and reapplying large language models or other black box models to custom data. It used to be possible in signal processing, right, to take an algorithm, even a complex algorithm, a complex beamforming method, high resolution music or Esprit or something. You take that, you have some data, and you apply it in the lab, and then you can study the limits of performance, you can improve performance, you can build understanding. That's no longer possible in this new era, where we have to deal with an impossibly large model, impossibly large data set, much of which was perhaps not even available, that is intellectual property, that was used to train, say, the GPT or OPT algorithms in large language models. And so the best we can do is, in these black box types of models, is something that is called calibration. Basically, you don't have access to the weights, the parameters, the tunable things inside the box. Just don't have access. Therefore, if you want to adapt a large model to your custom data, then the best you can do is basically try to adjust or calibrate the output of the black box. No access to the components, the individual components inside that black box. All right, so let me get started then. This is the optimized recalibration for pre-trained machine learning. And so as a contrast, a way to get started, just in setting notation a little bit, this was sort of the traditional machine learning framework up until a couple of years ago, where if you have a classifier, it's a function mapping f of theta, you know the mapping, you can adjust theta, you have access to training data that yields an output. In this case, we're going to be, for simplicity, specializing to binary classification, so that output y hat is a binary variable, or I'm going to be switching very soon to interpreting y hat actually as a probabilistic output. So instead of being binary, it's a value between 0 and 1, which represents the probability, posterior probability, that the label is a 1, right, given the data at the x at the input. So we could take a black box like this where we know the f theta. We don't know the training data that led to the choice of the weights, but we can retrain and hope that with using the optimized loss function that we can come up with a new model which is optimized for our data set using, for example, some optimizer which is an iterative optimizer like stochastic gradient ascent or some other first or second order method that generates a set of iterates, and maybe we do some early stopping to come up with what we might call fine-tuning of a model that for which we have access to all of the internal parameters. Okay, so that's sort of the framework where you might have a pre-trained classifier, but you have access to these parameters, and you have access to your custom data set or custom task for which you would like to fine-tune this model. So this traditional training framework is effective when we have certifiable accuracy, right? So certifiable accuracy meaning that we have some provable properties, positive properties of performance. So if you have a posterior probability that the label is equal to 1 given x, if you had that in hand, then you would probably want to use that because that minimizes the minimizes the probability of error, right? Of the Bayes probability of error of any classifier structure. So what we would like is that this early stopped retrained model f theta k of x is close to the posterior distribution, right, of the desired response given x. And of course, Bayes' rule tells us that that's simply extractable if you know the likelihood function, right? How the probability of x varies based on the value of the label and the prior on that label, right? So the important thing here for the future is when we look at cases where there might be disagreement between the label distribution or label proportion on the data which was used to pre-train the classifier and the data that we're trying to apply the classifier to, is that this Bayes rule basically specifies this posterior as a rational function of first order of the prior, right? So that's going to become important because since it's a first order rational function of the prior, probably y equals 1, this gives us a simple way to readjust or to correct for label proportion mismatch from the pre-training to the target data, right, that we're trying to match to. So requirements for a classifier like this to approximate this true posterior would be, well, first, we would like the loss function to be some good estimate of the 0-1 loss. That's the leads to the minimum probability of error classifier if you can minimize that loss over the class of functions, function mappings f theta k that describes this iterative early stopped approximation to the optimal class of error 1 classifier. But to do that, we need to make sure that this function f of theta belongs to some very expressive and rich function class. And of course, the more expressive you want this function class to be, that means the more parameters you're going to have to require. So this may require very large dimension, which will complicate the any optimization that might yield something close to the posterior, which if you have a large dimension of the model, it means you're going to have to even have a larger dimension of the training data, right? Which is typically impractical with these, large language models like GPT that have billions of parameters, and your data set, your custom data set, may not have billions of data points, right? You may only have some smaller number, like hundreds of thousands or millions, right? So the other issue is that we need to have a rapidly convergent iterative optimization algorithm if we want to stop early and be able to approximate this solution of the 0-1 loss function. So there are a lot of requirements here, right? And that's why the deficiency of the traditional training framework for these large models is really a big concern. So this just sort of states the obvious, since I've told you what we need in order for this approximation to the posterior of the output of this retrained classifier to be accurate, is that we may not have we might not be able to minimize the 0-1 loss. It's non-differentiable. It doesn't have a nice convex property. And so surrogate loss functions is probably what's used in place of that. There's probably a smaller class than a universal predictor class, right? The functions that you're going to optimize over may be the class of finite width, finite depth neural nets, right? Which can't possibly approximate any function, and in particular the posterior distribution, which is a function of x, right? Function of the input. There's small sample size issues, and then insufficient iterations. So these are certainly problems. But then another problem, which is separate from this, this problem of a mismatch of the output of the pre-trained classifier to the posterior distribution of the label given the input to that classifier, is that there's might be, and generally is, a mismatch between the distributions of the pre-trained classifier was trained on and the distribution of the target data, right? So a covariate shift or label proportion shift are two ways that this can occur, this mismatch can occur. Covariate shift meaning the class conditional distributions for the pre-trained model, the likelihoods given the labels of the feature sets have a different distribution, or some shift in distribution has occurred for the target data. And label proportion shift is when the priors are mismatched. There's a different proportion of positive and negative outcomes. And I'll show you a couple of examples of this in a minute. So these are very common factors in modern machine learning, and the solutions that that I'm going to talk about in a minute are probability calibration. That's what I just was discussing in the intro, domain adaptation, and then fine tuning. Take a drink of water here. So the contribution of this work is we have a unified approach, mathematical framing of this problem that's gives both geometric insight and also provides some optimal calibration rules for this handling both this calibration error relative to not having the true posterior of distribution, and also this this shift in, we're going to concentrate on label proportion shift. So this work is available on the archive, or it's also in the proceedings of the NeurIPS for 2023. Yeah. Sure. Right. So this is just looking at binary. This is just the binary case here, right? Yeah. Right. So I'm not considering the general case of multi-class. I'll have a few comments on that. But this is just the binary case for which we have a very nice, compact theoretical framework. Was there another question? Yeah, George. From the pre-trained data, all we have is the black box. Yeah. No. Don't even have the thetas. Yeah, so that's the, I'm going to differentiate that fine-tuning from calibration. Yeah. It's a unified calibration, unified theory of calibration. Fine-tuning is still wide open, and it's inapplicable if you don't have access to the thetas. So that. Yep, you still don't have access. You can't do a projection of any of the internal layers, right? LoRa does projections onto subspaces. Right, but you can't do that if you don't know the structure of the network. You don't know if it's a transformer, if it's a CNN, if it's an LSTM. You know nothing, right? All you know is that you can provide an input, and you can measure an output, and that output is the soft output, or the probabilistic prediction, right? Yeah. Thanks for clarifying this statement of the problem. Yeah, Nikos. Yes, that's my next slide. So, pre-training uses a lot of data, and you basically adjust all of the weights. You have a known structure. Fine-tuning is you have a much smaller set of data, and you use backpropagation to update some subset of the parameters. Maybe it's LoRa, right? Maybe it is maybe the first 3 or 4 layers. Linear probing, which is a restricted version of fine-tuning, assumes that you're only going to try and adjust the output layer, the final layer of the network. You're going to freeze all of the earlier layers and simply concentrate on the last layer, right? So you still have access to the weights, the thetas, for the last layer. And then recalibration, which is the only, as I say, alternative when you don't have access to any of the internal parameters, is we're going to apply what we call a recalibration function to the soft output. So this f of x, output of that black box, it's a value between 0 and 1. It's a function that maps maps the inputs to 0, 1, and that gives you some sort of distribution over 0, 1 over the entire target training set, and then we're going to apply a function that's going to distort, if you like, f, so that it looks more like the posterior distribution. Yes? Right. You may, but it doesn't matter. I mean, this theory doesn't matter, right? Yeah. But, well, that's the beauty here, is that the magic is it's a one dimension, you only have one parameter, right, at the output, right? It's simply the posterior distribution in the binary classification, okay? So we're going to end up having to estimate a function, a mapping from 0, 1 to 0, 1, which is a recalibration function, which is going to try to boost the output of this black box so that it looks more like the posterior distribution, right? All right, so even though this might seem to you to be a hopeless battle, right, to reduce the problem to just being able to map the output function, the probabilistic classification output, to some other function. It turns out that studies have shown that you can actually get much better performance if you don't retune a lot of the free parameters. Of course, we can't do so in the recalibration type of framework I was just mentioning. But even if you could have access to those parameters, there are cases, and these are some examples that come from a paper that was recently published on the archive, a tutorial, very nice tutorial on foundation models, of which this whole backdrop is a set, where if you do linear probing versus fine-tuning, for example, that basically tries to retrain the entire network, but maybe with some constraints, that you can do better in linear probing simply because you don't run the risk of forgetting, right? On this massive pre-trained data that you wipe out with fine-tuning potentially, or to a lesser extent linear probing. So you retain a lot of the structure and a lot of the parameter values that came from this very large data set. So, well, in this example, I mean, it's hard to say what it's really due to. It's either forgetting or it's the fact that the feature set actually doesn't shift very much relative to the pre-trained, but the model, the recalibration model shifts a little bit, right? So the labeled proportions, right? If you're going to use recalibration, these numbers are for the case where we do both this reshaping of the output in order to better approximate the posterior distribution, and we also use this rational function structure of Bayes' theorem in order to correct for different proportions. Right? So if you only have a shift in proportion and there's no shift in features, then this is a terrible thing to do, right? Because your feature representations are accurate in the pre-training data relative to your target data. Of course, you generally don't know that, but that's just one case where that's the case. So I was just saying, here's a bunch of reasons why you might want to use recalibration instead of fine-tuning. I'm not going to go through this. We've already talked about a lot of this before. This is an example just to make it very clear what we're doing. If this is the pre-training data, so there are 50 samples from class 1 and class 0, 25 each. It's an equal or balanced class pre-trained data set. And I've drawn from, in this case, I know that the data comes from a two-dimensional Gaussian mixture distribution, again, with class proportions that are equal, and the mean shift, and there's a variance shift between the two is known. Then we can write down the odds ratio, the log odds ratio, which is directly proportional to the posterior, and it has this simple form. And if you apply this to an imbalanced class, so this might be what the output is for the imbalanced shift in the feature distribution in this case, then you're going to run into a suboptimal log odds ratio, because it doesn't reflect the fact that we have a different proportionality and that we have effectively a shift in the variance, right? This just shows a sensitivity diagram. Just look at this red sensitivity curve. It's the relative odds ratio error, right? So it's that ratio of the posterior y equals 0 versus y equals 1. If you deviate from the balanced class assumption by any amount, you can see it's an extremely high slope. So there's lots of sensitivity here of that odds ratio, which means we better be careful about how we correct, right, for this shift in proportion. Okay, so here's a real-world example. There are a couple examples I just want to briefly put out here that motivated this study. One is, both of them are multimodal and high dimensional, is early prediction of infection susceptibility. There's several papers that we published. This is a couple of them. For this study, we had subjects who were wearing health watches that measured things like electrodermal activity, or resistance, I should say, accelerometer activity, heart rate, and so forth over time. And there's a pre-training segment where the subjects are healthy, and then at some point they get exposed to a pathogen and they catch the disease or not, right? They're infected or not. In this particular case, it's the common cold. And this particular subject developed symptoms, and you can see that those symptoms are clearly marked in the electrodermal conductivity, which is a measure of basically the salinity on the interface between the skin and the sensor that's in the smartwatch, measures perspiration. So the problem here is, obviously, the pre-trained set is not the same as the post-trained. So if you pre-train on these features, the post-trained is going to have a distribution that now has shifted due to the fact that the subjects have been exposed to a viral pathogen. So a pre-trained model is not going to perform very well for anomaly detection, for example, detection from the baseline of health in the downstream if there are things like baseline shifts that occur post-training. So this was one big motivation for developing this type of approach, recalibration, or in this paper we actually did a much more aggressive approach of adjusting the or fine-tuning the parameters of a known prediction model. Solar flare is another example that in solar flares you have, again, a prediction problem given a segment of time. In the past, you want to predict 24 hours ahead, and so you want to predict if there will be a solar flare of intensity greater than a particular threshold. So these are potentially very dangerous and disruptive of terrestrial systems, communication systems, energy grid, satellites, and so forth. So it's of interest to be able to do this kind of weather prediction on the sun. But again, there's a problem of covariate shift. This isn't really working here, is it? Okay, so this is just an example. So the covariate shift problem, I think I'm showing down here, is that if you look at the incidence of solar flares, this is in blue. These are the solar flares with their intensities. And you plot that over time, the solar flares occur with a frequency that is roughly periodic, with approximately 11 years periodicity. So this is the solar sun cycle. And so if you are learning in this region here to predict flares, well, the rate of flare production of this in red are simply the number of sunspots on the sun. Some of those sunspots, which are called active regions, will produce flares and some won't. But there are many fewer sunspots in the phase of the solar cycle that for which you have a solar minimum of sunspots. So there's clearly here a shift in the proportion of flares that are above a certain threshold in terms of their intensity, the so-called M and X class flares, depending on when you train. So if you train here and you apply the predictor in this region, then the frequencies are relatively equal. But if you apply your estimator, or predictor, I should say, down here for a pre-trained predictor that was learned during one of the high cycles, so I denote this with split 1 and split 2 up here, then you're going to be in trouble, right? There's clearly a shift. So this is dominated by label shift. Arguably, the feature distribution does not change. The class condition feature distribution does not change because the mechanism for producing solar flares is the same, right? So the features here are flux spatial and temporal flux measured from satellites. All right, so recap here is if you pre-train using some data dp with a distribution p, that p applies to both the response and the feature distributions. That's a joint probability. That produces some predictor f of x using, say, a neural network applied to this training data with distribution p. And then when you apply it to shifted out-of-sample data, which I call dq, has some different distribution q, the predictor can be mismatched either because of a shift of class conditional feature distribution, shift of label distribution, or in both cases, that produces a shift to the posterior. Right? And so that's why we're going to develop this recalibration approach directly to try and remap Q so that it resembles P for in the case of label shift. So I should say up here. And in terms of matching the posterior, we want to match these posterior distributions. Qy equals y given x to be matched to the actual output f of x trained on the data dq. Right? All right, so what does recalibration entail? As I said before, we're going to define a function h, which basically maps the probabilistic classifier value 0, 1 to different values, a different curve, if you like, over 0, 1, such that when you apply this function h to f of x, it gives you the posterior distribution under the target training data of label equal 1 given the input. All right, so we're going to assume, as I said before, there's no shift in feature conditional distribution. We're just going to look at shifts in prior label probability. And then this is in addition to the issue that even if you have the correct label distribution, that you may not be proportional, or you may not have a good approximation to the posterior distribution at the output of the black box. So in a nutshell, f of x, the output is not equal to the posterior on the pre-trained set. That's miscalibration. And it's not equal to the shifted posterior when you have label shift. And h is going to handle both of these simultaneously. And so you're going to take this curve h, which describes, in this case I use weather prediction as an example. F of x is, say, the Weatherman's predictor, right, given by very complex ensemble filtering of and generative models for weather development. And then you, as a user, you have your own distribution, your posterior distribution, which may be based on partially on what the weatherman says, right, and partially on what you see in terms of your own local conditions. Clouds in the sky. You may feel pain in your hip that you injured skiing a few years before. And so we want to find this H function that's going to map f of x closer to the posterior distribution on on your data set, right? On your local observations at home of what the weather looks like. All right, so that's in a nutshell what we're trying to do. As I said before, the posterior distribution is a rational function, and it turns out that the label shift can be corrected very simply by applying a function g. Z here is the output of the classifier. If we define f star as the posterior distribution, so let's say we did have a classifier that gave you exactly the conditional expectation of y given x in the binary case equal to posterior. It has lots of good properties, such as this one here. The label shift can be corrected by applying this function here, where W1 is the ratio of the posterior of y equals 1 under Q, that is in your target data, divided by what it was in the training data, P. And that assumes you know what the proportion was in the training data, right? So clearly you need to know that here. It also specifies f star, the posterior probability, the minimum probability of error decision rule, simply a threshold at 1/2, and you get the optimal decision rule for deciding between 0 and 1. This decision rule is an unbiased test in the sense of the ROC curve of this associated with the decision rule always lies above the diagonal, right, line. So that's another desirable property. It's also an unbiased estimate of the true proportion. So the expectation of the conditional expectation is the unconditional expectation, which is simply the proportion, right? So finally, this is the most important property for calibration, because this is what the calibration condition is going to be based on, is that the posterior distribution is itself a sufficient statistic for estimating the label, right? So if you condition on the posterior distribution, then the probability of the label being equal to y is equal to the posterior distribution, right? So f star x is a compression of x which loses no information about the label, right? So read a different way, this simply says f star of x, which we defined as the output of the black box, when you have a probabilistic classifier that yields the posterior, is equal to the conditional expectation of y given f star. F star is equal to the conditional expectation of y given f star is effectively what we call the perfect calibration condition, which is satisfied by this posterior distribution. All right, so there's the condition for a general f, not necessarily the conditional probability, but the output of your black box. So if your black box happens to give a probabilistic classification of f of x that is equal to the conditional expectation of the response variable y, the label, given f of x, then it's called perfectly calibrated, right? So this emulates the property 4, 3, and 2 that I just mentioned, right? So any classifier that satisfies this perfect calibration condition will be an unbiased test. It'll be an unbiased estimate, and it will mimic this sufficient statistic property that I just mentioned, right? That if you condition on f star of x, the label, you'll get f star of x back, right? Okay, so this is not our condition, but this goes back. I have a Gupta et al. reference here goes actually much further back to 2001, an ICML paper written by Zolodetsky. But that's the condition that we're going to be working with. Okay, so we're going to take, therefore, a arbitrary classifier function f of x, and we're going to try to find a function h that's going to make it closer to the posterior in the sense that it satisfies this perfect calibration condition, and it also has some geometric properties that I'm going to discuss in a minute, because this condition is relatively weak. For example, if you took f of x equal to a constant, don't discriminate either y, so always say y equals 1. This is going to be trivially satisfied, right? So, so that f of x is weak. Or let me amend that. If f of x is equal to a constant equal to expectation of y, not necessarily say it's 1 all the time. Say it's 1 at random with that random probability, the coin flip being heads equal to the probability of y equal 1. Right? All right, so here's where the geometry comes in. So bear with me a bit. So in meteorology in particular, there's something called the law of total variance. And what it says is that if you look at the variance of y, which is the expectation of y minus the expectation of y squared quantity, right? So that's the length of this vector here between expectation of y and y. It says that that's decomposed into two components. It's decomposed into the variance of the expectation of y given z. So the expectation of y given z, the variance of that is the expectation of y given z, given its expectation, which is the expectation of y. So it's this geometric vector in this vector space of functions of z. The z here, don't forget, is f of x. And then it's also, there's another component, which is the expected value of the variance of y given z, which is this term here. So respectively, this component is called the explained variance, the so-called sharpness. It's what you can explain using any function of your output z, right, of the classifier. And then the refinement is the orthogonal component, which is not explainable by your output z, any function of the output h of z, for example. All right, so that is a decomposition of the variance of y, the law of total variance, into sharpness and refinement. That's going to become important. But it's not the main point here, which is that we have a decomposition of the so-called recalibration risk, which is what I'm showing up here. That's if you have z. Well, first of all, let me just go to the. Let me just say here in words that this risk we're going to target for choosing h is can be decomposed into the sum of what we call a calibration and this sharpness risk. And what that corresponds to, I'll explain sort of more slowly in this sequence of geometric pictures. So we have z, the output of our neural network, let's say. We would love it if z was equal to the expectation of y given z, because we know that that is among all the functions of z that you could possibly choose, is the one that minimizes the distance squared to y, right? But we don't necessarily satisfy that condition, right? That's the whole point. We don't necessarily satisfy the calibration condition, and that's why we have a finite length. Is that difference? On the other hand, we posit that if we make some mapping of z to another output, right, of the probabilistic classifier, that output h of z is going to lie on this subspace. It's a function of z, so it's a subspace that one such function is expectation of y. And now what we have is a hopefully closer estimate of of y with h of z. But more importantly, we are able to better approximate in terms of excess risk, which I'm showing right here. This is the excess risk relative to what you'd be able to achieve if you use the true posterior given z to classify y. It's the excess risk for using h of z. And what we're hoping is that that will be smaller than the excess risk if you use z. Right? So what the whole purpose is to make this h of z closer to this expectation of y given z. Well, there's a decomposition theorem, that's the one I just gave in mathematically, that says that this excess risk, Rh, can be decomposed into two risks. The sharpness risk, which measures how far away the posterior distribution of y given h is from the posterior of y given z. We'd like that to be small. And then the calibration sharpness risk, which is how close to h, how close does this perfect calibration condition hold? That is, how close is conditional expectation of y given h to h itself, right? So we can decompose it into two. Okay, I'm almost ready to finish here. So that's the theorem. Excuse me, that's the decomposition. So what we have now is an algorithm that allows us to attack this problem choosing this h. And I'm just going to give, because I ran out of time, a quick overview of what this function is. The function that we want, and I can't go into details, is a function h that effectively makes the distribution of the data given each value of y equals 1 or 0, makes that distribution uniform. I can't go into why that's the case, but this is something that was shown actually many years ago. And so what we do then to make that uniform, how do you make a distribution uniform? Well, you can take order statistics. In this case, we do jump order statistics, take every 4, let's say, outcomes on f of x. So these are at different fxi's. And then draw a histogram that basically then aggregates in each one of these bins. This is called uniform mass binning. These fxi's, these outputs, and then associates the average label assigned from those outputs. And that, it turns out, is asymptotically optimal if you have lots of measurements from your target distribution. And we have a theorem on this. You can go to the paper to see we have a decomposition with the decomposition of the calibration error risk, and the sharpness risk. This is like a variance bias trade-off. And we can optimize that trade-off relative to the choice of the number of bins that we use in this histogram. So the number of samples per bin that are that's fixed, right? And we can optimize that. What we find is that there's an optimal bin size, which is take the number of samples in your target data set and the third root of that times some other terms, and that gives you the best binning. And given that best binning, we get a sample complexity, which tells you that your sample complexity only has to, the number of samples only has to increase as epsilon, where epsilon is the accuracy, 1 minus the accuracy raised to the -3/2 power. All right, so that's that's really all I have to say here. We have some other results that you can go to the NeurIPS paper, and my conclusions are simply that we have a framework for analyzing recalibration with this decomposition into calibration and precision. We can call that sharpness. I call that precision here, but it's sharpness. We have this risk upper bound. We have this optimal number of bins that occurs from an analysis of that upper bound, and we have a recalibration under label shift. Future directions, multi-class classifiers is a much more difficult problem, because now instead of having a single function you have to calibrate, you have multiple functions. You have M classes. It's M minus 1 dimensional problem in terms of class probabilities for every class minus 1. And then the problems of online recalibration. We have streaming data. It's also a direction of interest. So this just describes some of the contributions in a more direct way, and I'll just end there. Thank you for listening.
We can take one quick question.
And I'm here for the duration.
So I was wondering how do you use this theory for a single sample case? If there's only zero-shot learning, for example, like you can't use this. And what is
there's no, the theory doesn't.
Yeah, exactly. So, what is a minimum n required for applying this theory?
So, in the bounds that we derive, these are concentration bounds.
Okay.
The minimum number of n for those bounds to become tight depends upon, not surprisingly, the true value of the optimal h.
True value.
The true function.
Okay,
right?
okay, okay.
There is a true function that you can solve an optimization problem that if that function is smooth, then you require relatively
fewer
samples.
samples.
If it's very highly varying, then it's like any problem, right?
Right.
Function estimation. Function estimation has very high bandwidth, highly time varying. You need a lot more samples to estimate that function. Yeah.
So and you
can't answer your question with a quantitative.
Okay. So you call the refinement operator as precision, but I wonder why you call it precision.
Only because if you minimize refinement, you're minimizing the unexplained variance, and therefore improving the precision of your class.
Okay. So it's
right. In that sense, improves precision because the posterior because y becomes closer to the explainable subset. Right.
Okay. Right. Okay. Thank you.
Okay. So thank you, Professor Hiro, for the exciting talk. So our next speaker is Dr. Brian Sadler from UT Austin, and he is going to talk about hierarchical reinforcement learning. Welcome, Dr. Sadler. So.
I did. No one took it from me, so I just walked away with it.
Thank you. Good. Thank you. So thanks to the organizers, as everyone has said. A lot of people look at me when they discuss ARL, although I left there a year ago. So This work that I'm going to talk briefly about, it's relatively recent interest, and I think this bottom line up front is that hierarchical reinforcement learning is very difficult without a lot of prior knowledge. So if you want to do this data-driven and you introduce these hierarchies, you open up a sort of new envelope of issues. And I'm going to talk a little bit about that and a little bit about some approaches to try and handle that. And acknowledgement to my, my collaborators, including Amrit, who worked with me at the lab and is now a professor at Central Florida, and he came from IIT. And so hierarchies are well motivated in many problems, right? We love modularity. You know, and as I like to say, and now that we're in the machine learning era, we're all becoming systems engineers and computer scientists, right? I was reviewing an ICML paper, and it was so complicated with so many pieces, they couldn't describe it in the 8 pages with the appendix. You had to go look at other materials just to kind of get a sense of what's going on. So that's an aside, but we like modularity. And hierarchies are very natural for a lot of problems, right? A lot of engineering problems. And so it's appealing for control especially. And so most of the guys that I'm working with at UT come out of autonomy control kind of space. And the examples I'll show you here are with simulated manipulation kind of task. A few things you can do with these, you can have different timescales running, right? So you could have some lower level tasks that run, and then some, say, longer time scale running over top of that, directing tasks. And this is a kind of major motivator for this hierarchical approach in controls in general. But you can have abstractions in various ways. It could be temporal, it could be spatial, and so on. And it may be appealing for transfer learning. So the kind of things I'm going to show you with single task level at the bottom and a manager at the top. But you could imagine having many tasks, and composing those tasks would be the manager's job of selecting, and right, and that's appealing from a transfer learning perspective, because I might have many tasks, and I learn to recompose them for some new kind of behavior desired. So the basic setup is like classical reinforcement learning and MDP, some forgetting factor, you have state action space, you have our reward, but now we're going to split it into 2 levels. And most of the work in this area is bi-level. I would say bi-level is not really fully solved. And it's just like bi-level optimization, which is a nice theme in signal processing. It's hard to go beyond that. When you have coupling that goes up and down multiple layers, these problems become very challenging. But if you look at bi-level signal processing optimization related ideas, they're pretty, there's a pretty good variety of solutions and theories there when you're doing these kind of cross-level optimizations. Not necessarily true here, and I'll show you why. So at the higher level, the idea is that I have this manager operating on his own time scale, and his goal is to give the worker, the guy who's actually working in the state action space, a sub-goal. Okay, so keep in mind, we're trying to learn the entire process here. So the manager is trying to learn how to direct, while the guy at the lower level is trying to learn to do a task. So this is especially a problem when you have sparse reward. Okay, so we're going to go through some complicated process and hit that reward. The manager is trying to set sub-goals as the lower level task, the lower level task guy learns to hit sub-goals, and eventually that back and forth leads us to a behavior which gets us to the total goal. And then the lower level looks more like a conventional RL problem. I've got a state action space. So a couple things to note here. One is typically I use off policy. You go to an off policy reinforcement learning approach so they can reuse your data. And it becomes really critical here because this going back and forth across levels really expands your need for data. Okay? and yeah, goal conditioned. So we can go into that a little bit deeper. So at the high level, I've got this policy which is depending on the reward over a state goal trajectory. And here G star is the final goal. So keep in mind now that what I'm trying to maximize here is this guy so that I get an optimal sub-goal predictor. Okay? I'm not trying to maximize like you're doing down here, where I'm trying to, over this finite horizon, I'm trying to maximize the expected reward that I get over a trajectory. It's common in these problems to use an entropy regularization. This is entropy on the policy. And the purpose of that is it does encourage some, you can think of it as, in exploration, you would think of entropy as encouraging some little bit of randomness in the behavior. But in problems like this, there may be more than one perfectly good solution. So you don't want to converge to a policy which just always says this is the solution. There may be multiple solutions which are good, and you'd like to find those. Yeah, so the notation here is that GT is the sub-goal from the higher level policy, right? And then the lower level action, he's got that sub-goal now, and that's what he's going to work with. Now you can phrase this as a bi-level optimization. But you stare at this a little bit and you realize, well, you know, you have these problems, and when you bi-level optimize, I'm optimizing and putting back this and optimizing, and pretty soon I've got this, you know, very, you know, I've got this, right? This guy's assuming I've got the optimal low-level policy, but we're doing this over episodes where I'm going to a sub-goal, and then I assume you've got the optimal policy to get to the sub, right? So, so it's a little bit funny here, and we have a significant non-stationarity going, and I'll talk a little bit more about that. So the question is, how do you build this stable approach to doing this from a learning perspective, and how do you do this when you're largely data-driven? The aside is that, you know, there are a lot of papers, and there are papers in signal processing literature using hierarchical. Usually this means that, say at the lower level, we have some, you know, specific parametric model, or I have something I'm going to optimize in a more conventional signal processing setting. So the level of learning in problems like that is significantly different than when we're fully generalized. In the learning literature, they don't say prior knowledge, they say expert. You have expert knowledge. So here's a couple of issues. And so one is that if the higher level policy, so the low level policy is it's learned a certain amount, and the higher level guy now is going to give him a new sub-goal to go for. But if he gives him a sub-goal which is infeasible or too hard to get to, then we have a significant problem. So the picture here is designed to say that, well, I've given you that sub-goal, but maybe you don't have a sufficiently sophisticated policy to get around the barrier yet. Right? So you can easily give sub-goals which are unachievable by the current state of the lower level policy. So you can be too conservative in this space too, and that just lengthens out your learning time. The other thing is that because of this policies that are evolving on both levels, then then the reward becomes obsolete. So we have a kind of non-stationarity going on because we're learning the reward as well. Right? So this is especially true for sparse. All right, so looking at these two things, I'll give you a couple of ideas that we've looked at for trying to deal with this. So, you know, there's a huge amount of success with human preference optimization. If you know a little bit of the history of the large models like the LLMs, for guys I've talked to in the industry, they said, well, you know, we came up with this big model and we trained it on, you know, Wikipedia or something even vaster, millions and millions of data points. And then it was still giving you these funny, you know, you put in a written query and you get this thing, and you'd say, but that's not really written in a way that I would say is a nice. So they started introducing human preference optimization into that. The interesting thing was that 5, 10, 20,000 updates based on human input over the millions that you've done, right? So this is a kind of fine-tuning using human preference was extremely valuable. All of a sudden they had something which they felt like was a marketable product. So that, that clearly showed the value of it. You can do the same thing here in the sense that you could use human preference at the higher level to learn the higher level reward subgoal generator. But we thought, well, can we use the preference idea but do it automatically? So the idea here is that we're going to compare two higher level trajectories. So here's a trajectory state action. Keep in mind this is going on up here in the higher level. And our goal is to learn a function which is the reward function for the high level guy. Okay, so we don't know what his reward is because, right, we're trying to learn how to generate the subgoal. So we look over trajectories and we can write a probability where this is the neural network parameterized by phi. And so here's our cost function that we're trying to minimize with respect to this neural network. Yes? That's right. So the lower level, think of the lower level guy as a conventional RL. He gets his reward from state action in the environment. Yeah. Correct. Yeah. Yeah, although this is, so you could think of this at the higher level, it's almost like a planning, right? Because I'm looking, the higher level guy's reasoning about where if the lower level guy's at a certain state, if I look at thinking about trajectories towards a subgoal, okay? So remember the higher level policy is trying to get a subgoal, which is either going to pass down to the lower level policy. So how does he learn to do that? He can look at it from a trajectory point of view. Say it again. Yeah, so when I give a subgoal to the lower level agent, I'm making at that stage the reinforcement learning problem much simpler by just saying, okay, here's a subgoal. Learn how to get to that. And it's sort of like piecing right. I'm piecing trajectories together through the state space for him. Okay, so we can do this, and one of the important things about off policy is that you can reuse your data, but we have to relabel the. When you do this, you need to. In our case, if you're going to use old data, you've got to update the reward for that. Okay? So this is called hindsight relabeling, and because the old reward can become pretty out of date pretty fast. Okay. So that's an idea which is helping at the higher level. But I still have this question of the connectivity between the low and the high, because when I go to predict a subgoal for the lower level, I should take into account something about the current lower level policy, because that's evolving. So the idea here is that we augment the reward with a regularization which is based on the current value function of the lower level policy. So this is like saying, okay, if I know the value level, if this is kind of telling me about how well I think it can get to a particular subgoal. Now, this regularization turns out to be quite useful and valuable, but it is going to be sensitive to this tuning parameter. And one of the issues in this hierarchical world is that the hyperparameters can be quite sensitive to the hyperparameters. You have the same general method. You change something about what the problem is and so on, and you're kind of back to square one in terms of where the hyperparameter is. And this is something that plagues this field at this point, I would say. Yeah, so this is the overall goal. That's fixed, right? So the reward for the way we compare the trajectories at the higher level is based on a trajectory through state action, right? And that's what this gives me. But when I look at, so the GT here is the sub goal I'm trying to get. Okay. That's right. Yeah, I know the notation is a little, yeah. Especially when you're trying to go fast and we can go have tea. Okay, so that's a couple of ideas. You know, one is really trying to regularize the sub-goal choice with respect to the current state of the lower level policy, because we're doing this episodically back and forth. And then the other is to affect how we're going to do the replay here and bring in this idea of sort of an automated preference optimization. It's interesting, when you say preference optimization, people automatically assume a human. Okay, so simulations. So this is a variety of robot arm kind of tasks. This is a very simple task. Move to the target, pick up an object and move it to the target. Here, push the object to the target. Hollow refers to it. You have a hollow object. And in the kitchen one, this is a little more complicated. The idea here was to open the oven, pick an item, put it in. Right? So it's a little more advanced. None of these, you'd say, are super highly complicated control objectives. Putting this all together, by the way, this is based on a ICML 24 paper, ICML paper from last year. So if you search on Piper, you'll find it. So the primitive informed means that we're regularizing based on the primitive, which is the lower level. The preference based is we're using this idea of preference optimization at the higher level. And then we're using that to try and do intelligent relabeling. Okay, so just a few charts. So this is showing success rate against time steps for a few different tasks, comparing to a variety of, some of these are hierarchical and some of them are not. So you could think of this as just increasing the task complexity. When you get out here to the hollow and the kitchen, the only guys left standing basically are these. This is ours without the regularization. So this is not regularizing using the current state of the lower level policy. And these do pretty good. It's also interesting to look at the variance. So if you take out the regularization, like in this example, you could see that you can get complete failure in a case like this because you didn't do the regularization. And yet for these tasks, maybe it acts as a variance reducer. So so it's interesting to compare to an example from the literature where they took one of these tasks and they tried to handcraft the reward. This is common in reinforcement learning, of course. It's, well, I'll just fill in the rewards somehow, handcraft that, and as a means of prior knowledge. And we get this kind of interesting mix. Again, we're going from something which is relatively simpler to more complex. And for this problem, having these sort of predefined reward function was good, but then eventually it didn't really work, especially as we get to something which is sort of multi-staged behavior. And then I mentioned this hyperparameter sensitivity. So this is the sensitivity, this is time step, success rate, the sensitivity to the parameter alpha. So how strongly we're regulating on the current lower level policy. And this is changing by orders of magnitude. So a couple of things you said, all we're running is our method now, Piper. So you see that the sort of variation that you get, the amount of variation you get here with respect to the hyperparameter depends on the task. This is not unusual in this space of hierarchical problems. And it can, if you get the parameter right, it can really help you quite a lot. Conclusion. So I showed you some attempts at getting a little more stability into fully data-driven learning for this hierarchical problem, specifically where I have a manager and a task at the lower level. And these problems of non-stationarity and how you go back and forth are bedeviling, even though the method is very appealing. So I mentioned the reference. So there's a couple things I think that are interesting as follow-ons. One is that there's a lot of work in RL in general as you go up in dimensionality in the state and action space to look at abstractions. So you can do various things to abstract the state down, and this accelerates your learning because the learning, the learning sizes here are very significant. So that, it seems to me, would be interesting maybe in the context of what we're doing. And then, since this is a signal processing and machine learning workshop, I think that this is a recent, something we've recently been looking at is starting the problem as a bi-level optimization and then going from there. See what we can derive as far as we're trying to get to a bi-level optimization framework now. I think this is interesting. It's got a lot of potential. And I also think it's if I step back on this problem, the problem is very hard because you're really trying to learn everything. And if you were going to engineer or something like this, you wouldn't do it this way, of course. The fundamental questions are, how far can we get with something like this? And how do we make this trade-off between bringing in some expert knowledge or not? As Yorgo told me one time, and this was, I don't know, I think it was around 1992, and neural networks were starting to make a big run. And he said, neural networks, he says, that's what you do when you don't know what else to do. And we were so keen on what knowledge do we have, what functionality do we have, what parametric model do we have, right? So I think ultimately the question from an SP perspective is, as I go to apply this maybe in a SP framework, what parametric models am I bringing in? Does the manager task kind of framework make sense? And then the learning certainly gets a lot easier. And I think if we phrase this, I'm hoping phrasing this through the bi-level optimization framework will lead us to some interesting places. So that's my talk. Yeah. Yeah, we have the same thing here.
Fast learning rate at the bottom, and then it's fairly slow at the top, so it's successive hierarchical.
Yeah.
So is the analogy here that there is an allocation of the exploration versus exploitation trade-off is fundamentally different at different hierarchical levels? So, imagine an exploration could be very costly to the state at the higher level, right? But maybe at the lower level, well, it's not, because the task is less complicated.
So the thinking here is that whatever the time scale at the lower level is, I'm going to give you a sub-goal which is reasonable for you. Okay, so that's the first separation, right? But as you stack on more and more sophisticated behaviors, to learn the whole thing from the get-go is, right? I mean, this is not super sophisticated kind of thing we're doing here. So I think the ultimate answer will be, an approach, right, is to, you train guys for certain tasks, and then you try to build them up. And how do you do that, right? I think I like this problem because it's a really fundamental question. Here you've got this data, and you go back and forth. But I think so your question about time scaling is, I agree, you can manipulate that however it makes sense for you. And state space too, and you can use abstractions. Like some people in this kind of setup, they'll come up with a multi-agent problem for the lower level and try and do that for a while and then add met, right? It starts to look like a meta-learning problem. I have a behavior, and then I'm just going to switch between them based on some context, right? But here we're really composing. If I want to do some complicated thing, I've got to compose through task space somehow. And that's motivated by, a lot of it by transfer learning. Yeah. T-John?
Any other question? Yeah.
I guess the other question is, at the lower level, you may have benefits. You have multiple agents, a peer-to-peer.
Yeah, yes.
So, and then the upper level doesn't really have to intervene until there's some sort of limit cycle or, there's a lack of consensus. I hate that word.
So what you're saying is that, we can solve a lot of this with a multi-agent architecture.
Right.
It may even be that I don't need to think manager workers. I could just think multi-agent. To me, the more I think about this, I think if I had to throw away this, then I'm really probably competing against some kind of multi-agent approach, right? And that might be much more efficient in the end. So, yeah. I think that's another nice thing about this is we haven't settled in on even how to approach these problems. Yeah, so, all right.
So I have a question, how much separately these higher level and lower levels are? Is there any in-between thing that can also be overlapping layer between them?
So they're separate entities,
Okay.
right? They have we're defining two different policies. They both see the state action space, but what's going from the upper to the lower is the sub-goal. Okay. So they're really like two separate policies that are interacting through this.
But can we always have this kind of an approach? That we have two separate policies and...
This is an approach.
Okay. Yeah.
Right. And as Al was saying, there may be better approaches. Yeah. I think it's clearly nicely motivated approach, but does this one ultimately make sense? Because if you don't have much prior knowledge, then it's very challenging. Yeah. Right.
There is no other question, then let's thank Dr. Sadler. Actually our tea session has already started, so maybe we can go for tea and come back by 5. So the next talk will be at 5 p.m. So please come back before that.